Welcome back, students. This is going to be our third set of lectures in the unit of kinetics. In this section, we're going to talk about the involvement of energy, and we're going to be setting up the stage for us to discuss later on reaction mechanisms. Okay, so let's go. Okay, students, at the end of our previous lesson, we learned several things about the rate of chemical reactions. So let's summarize. Let's consider reaction A being converted to B, where the small letters represent the stoichiometric coefficients. From an experiment where we are measuring changes in the concentration of either reactant or product over time, we can arrive at an expression like this one, or an expression like this one, where delta A over delta T or delta B over delta T represents the change in the concentration of that particular species. And then you see that the negative sign represents that the reactant is disappearing, quote unquote. And then you have to compensate for the fact that because the stoichiometric ratios are different, they might not show up or disappear at the same exact rate. This is what we call the rate expression, and like I said, it is based on what we actually measure in an experiment, the change in concentration over time. Now, from experiments where we measure the initial rates at varying concentrations of reactant, we can arrive at an expression that looks like this. Rate equals K times A to the X power. This is what we call the rate law, where X is the reaction order and K is the rate constant. And remember, the value of X, the reaction order, is not necessarily the same as the stoichiometric coefficient. The rate law has to be determined experimentally. Now, what is this useful for? Well, besides other things that we discussed in the previous lecture to set us up for what's ahead, let's say that the rate law is useful for studying reaction mechanisms. In other words, what are the steps by which the chemical reaction happens? Now, when we look at chemical reactions, we observe one outstanding thing. Why are many chemical reactions so slow? For example, if you take a steel nail and you apply a flame to it, hardly anything happens. Maybe it'll bend. If the flame is hot enough, you'll start melting the steel. But if instead of a steel nail, we have a bundle of steel wool, then what will happen is the following. So why are some chemical reactions slower than others? Please forgive me and indulge me in a little illustration here. It comes from one of the icons of our generation, the great Tony Hawk, right? If you grow up or live in the suburbs, you might see some of these skate parks where kids love to go out there and skateboarding, and they do their tricks. They do other kinds of tricks, like standing on a wall there on the edge. It's a different story when they bring it out into the streets, right? And some of the things they do are kind of like, a little daunting, but some of them are downright scary. It's a different story, like I said, when they are doing these things outside of the confines of a safe skate park. Now, some cities are very welcoming. For example, I think this is in 2019, Long Beach hosted a skateboard fest, and the streets were crowded with a bunch of kids in their skateboards. Now, like I said, it's a different story when you are growing up in or living in the suburbs. Particularly in my case, many of my friends lived in South Orange County in some of these very, particular special communities. Let me tell you about that. So,
I've lived in Orange County for about 20 years and I have many friends all over the place. My neighborhood was okay, but there are several neighborhoods in South Orange County where the neighbors are quite picky and the homeowners associations are, pretty powerful. And so this friend of mine lived in a neighborhood where there was this street that had a nice little downhill slope. And of course, all the teens in the area loved to go skateboarding there because you simply go to the top of the street and then basically just let the momentum, let gravity take them down. They love that place. But of course, you know how it is with teens, they make a lot of noise. And so some of the neighbors were kind of like concerned, not about the safety of the teenagers, but really about the noise and the commotion around there. So the homeowners association decided to take action. And what they came up with was to put these kind of like small, like, maybe 3 foot barriers at the top of the street to, I guess, discourage the teenagers from, using that as their launching pad. But of course, you know, a teen with a skateboard will not be denied. So let me tell you what they did.
Of course, the teenagers faced what seemed to be a daunting task, but what was meant to be a deterrent, that small wall at the top of the street, actually became an inspiration. So, remember the tricks they learned at the skate park? Like they could basically walk up to the top and then skate very fast towards the little wall, and then of course kick the back of their skateboard, make a big jump, and then of course land right on the ledge of that little wall, just like they learned at the skate park. And then it was a matter of just leaning forward and sliding down the street. So basically, the small wall did not stop them, it just slowed them down a little bit.
And that is a true story. Let's see how we apply it to our study of chemical kinetics.
So the point to take from this story is that notice that in thinking about these kids trying to go down the street with their skateboards, even when the homeowners association put up those barriers, it didn't keep them from doing it. It just slowed them down a little bit. So it leads us to think that perhaps the reason why many chemical reactions are slower is because there must be some barrier, some kind of hill to climb over in order to go from reactants to products. And that is the case. Let's see if you remember the importance of energy in all chemical processes. And specifically, we're going to introduce the topic of activation energy. So here is a typical energy diagram for an exothermic reaction. And maybe you remember, let me put it in here. You have on the x-axis, you have the reaction progress. This is kind of like you're tracking how the reaction is coming along. And then in the y-axis, you are tracking the potential energy. Let's say that A and B are the reactants, and C and D are the products. So we have seen this before, right? We are accustomed to seeing these diagrams, and we know that the difference in energy between the reactants and the products is the change in energy of the reaction. For most chemical reactions that are done at constant pressure, this would be the change in the enthalpy, commonly referred to as the heat of the reaction. Now, let's say that we look at an endothermic reaction. Notice that in the first case on the left, the products have less energy than the reactants, and therefore the difference is going to be negative. There is heat being released out into the surroundings. In the case on the right, again, we have the change in energy from reactants to products. This would also be the delta H, or the heat of reaction. Again, notice that because in this case the products have a higher energy than the reactants, the system essentially gains energy, which is going to borrow it from the surroundings, and so it is an endothermic reaction. Now let me point out to this little thing here, the activation energy, E sub A. This is essentially the minimum amount of energy required to initiate a chemical reaction. Notice that it is technically the difference between the energy level of the reactants and the maximum energy of this peak, this hill that the reaction has to overcome. At the peak of that energy profile is a species, which I'm kind of representing here as AB double dagger. This is what we call the activated complex, sometimes also referred to as the transition state, although in more advanced courses, we do separate those two concepts. Essentially, this is a complex, a species where the reactants are kind of like in the midst of the transition. They are about to become products, and they're in the midst of undergoing the changes that are going to have to take in order for them to be converted into products. So if we were to write the actual reaction, including this intermediate, top of the hill kind of state, we would say that A plus B, the reactants, are first transitioning through this activated complex before they can become products C and D. Notice that the steeper, or let's say the higher this hill is, it's not that the reaction cannot happen, it's just that it's going to take a lot more energy to get the reaction going. In the same way that, I told you about the kids on the skateboards, once they climb on top of that little barrier, all they had to do was lean forward, and they would drop down to the street and continue on their merry way down the bottom of the street in their skateboards. In the same way, reactants have to reach this state. We had to climb this hill before they can undergo the rest of the reaction. And so the idea here is that the activation energy is going to determine how fast or slow a reaction is. The higher the hill to climb, the slower the reaction. Now, I would have loved to show you this video, but unfortunately, my access got taken away. And so what I'm going to do is close us out here, this little section here, with a little practice exercise, okay? So I want you to look at the question here. Which of these reactions would we expect to be faster? I'm going to show you the picture, and then I want you to maybe pause the video and see if you can answer the question. There are 3 energy diagrams. Again, it's not specified, but the bottom, the x-axis, is the progress of the reaction. And you can see there, you had to decide, okay, how do I determine which one is the faster of them? Fastest, I'm sorry. Okay, so what we would say is we look not at the actual change in energy between reactants and products, but at the size of that hill. And notice that if you look at reaction number 1, the activation energy for that reaction is 15 kilojoules per mole versus 25 for reaction 2 and 20 for reaction 3. Therefore, the one that should be faster is the one that has the smallest hill to climb, and that would be number 1. Okay, now that we have this idea, we're going to explain what is the source, what causes this activation energy, and how is it related to the rate equations that we have built before. So we'll continue this in the next section.